Seriously? Here. Okay.
Excellent.
All right, now. All right, so let's play. Okay, so do I even have a, no, I don't even have, I can't even see my cursor. Okay, so I'm going to talk about this in terms of discrete dynamical systems, right? So everything I say about discrete dynamical systems also applies to flows. It's just
you were okay until the you had the long rectangle as the attractor.
Oh, okay, good. So I didn't lose
Yes.
everything until here.
Yes.
Okay, good. Okay, so let's just review the long rectangle. Okay, so the long rectangle here, if I look at the forward image of that, it's inside this rectangle. And if I look at the maximum variance set, the set of all orbits that stay inside this rectangle, it includes not just the 3 equilibrium points, but also the connecting orbits between them. And so it's important to realize that the omega limit set of a set is not just the union of the omega limit sets of the individual orbits, which is the 3, any individual orbit limits on one of the equilibrium points, but it contains these connecting orbits in between. So I want to express that attractors form a lattice. So we're going to talk about bounded distributive lattices here. And a lattice is a collection of objects where they have 2 binary operations, meet and adjoin. So the kind of wedge and V. And when you're thinking about bounded distributed lattices, you're perfectly fine thinking about a finite collection of sets and intersection and union, because there's a theorem that says that any finite distributed lattice is isomorphic to a ring of sets where under intersection and union. So you could think of it as just that way, right? And so the idea here is that not only are the attractors going to form a lattice, but the attracting blocks are also going to form a lattice. And so we're going to have 2 lattices, the lattice of attracting blocks of F and the lattice of attractors F. And the way, as Constantine was saying, the way you want to think about this from the point of view of Conley is the attracting blocks are the things that are robust under perturbation. So if you understand attracting blocks for a particular parameter value, if you or a particular system and you tweak the system a little bit, then there's still attracting blocks if you're sufficiently close. Whereas attractors can bifurcate and change in complicated ways as you tweak the system, right? But you know, we think of starting with attractors from the point of view of global dynamics because attractors are, in some sense, the things that we can observe, right? And so the main idea, the kind of big picture that underlies what I'm going to talk about is that you can think of having an algebraic model of global dynamics as having these 2 lattices, bounded distributed lattices of attracting blocks where the operations are union and intersection, and then of attractors where the operation, the join operation is union, but the meet operation is a little bit more subtle because of the lack of invertibility of the system. I can't just take the intersection of the 2 attractors to get an attractor. I have to take the omega limit set of the intersection, okay? But that still can be proved to be a bounded distributed lattice. And the application of omega limit sets, taking an attracting block and looking at its omega limit set or the maximum variance set in that attracting block, that becomes a lattice homomorphism between these 2 lattices. It's surjective. Okay? And so there's an algebra that is behind these constructions. So what does that look like in a picture? So if I look at what the lattices look like from the example that I just did, so the lattice on the left is the lattice of attracting blocks where I have the empty set at the bottom and I have the 2 squares there, and then their union. So I have the union of the 2 squares, and then I have the bigger rectangle, right? And if I apply the omega limit set homomorphism, I get the attractor lattice over on the other side that has the 2 stable equilibrium points as individual attractors, then their union, and then all of the equilibrium points with the connecting orbits, right? And so omega limit set here is a lattice homomorphism. In this case, it's an isomorphism, but I'll do an example in a little bit where that's not the case. Okay. So how does this then connect up with the idea of a Morsi composition? So suppose you could compute something like this, starting from, as Constantine was saying, and I'll explain a little bit, starting from some sort of cubicle or decomposition or triangulation of your space, and you were able to identify a attracting block lattice of some type, right? Then how can you get to understanding Morse decompositions from this? Well, there's a notion in a lattice of a join irreducible element. And I put the formal definition here and you can read it, but basically the key thing to understand about a join irreducible element is that it is an element in the lattice that has a unique predecessor. So every bounded distributed lattice is a poset based on the inclusion here, right? So you can think of these are sets. So you can think of the order on here is ordered by inclusion. And the join irreducible elements are the ones that have unique predecessors. So for example, each individual square is a join irreducible because the empty set is a unique predecessor. The union of the two has two predecessors, so it's not join irreducible. And then the top big rectangle is join irreducible because it has a single predecessor, right? So these join irreducible elements form a poset that you can pull out of your lattice. And when you have this omega homomorphism going across here, then when you apply this join irreducible operation to it, it's actually a functor, and you get an order embedding back from the attractors into the attracting blocks, right? From these structures. So then the idea, so here we have, it's really like a pointer, but I can't. Okay, so we have these things as attractors, right? So attractors are not this thing on the right here with the red sets. This is not a Morse decomposition, right? So these are actual attractors. So how do we actually pull out a Morse decomposition from this? Meaning, what is the Morse decomposition of this system going to be? Well, it's going to be the three equilibrium points, right? With this middle equilibrium point sitting above the other two, the saddle point sitting above the other two, right? We have a bistable system here. So how do we do that? Well, with Rob van der Vorst and Constantine, we've developed some theory for something called the Connolly form. And I'm not going to go into all the details of that, but basically it's generalizing the idea of a set difference operator that's really only defined, standard set difference is only defined on a Boolean algebra. And we have here something that's not a Boolean algebra, but you can still extend the definition of set difference to bounded distributed lattices. And you can recognize that set difference and represent it in different representations. So for example, you can look at the set difference between two attracting blocks and realize it in isolating neighborhoods. And you can look at the set difference of two attractors and realize it as an invariant set. And so when you do that, in this case, and I'll show the example, the slide and shows what happens in this example, you get what we call a Morse representation, which is a post-set of invariant sets, which are the Morse sets. And it's kind of dual, it's dual to this finite attractor lattice, right? So here's the picture. So you take the attracting block and you look at the unique predecessor, because it's a join irreducible, it has a unique predecessor, and you look at basically the set difference of that. And so that's that little isolating neighborhood that's in between, that's the piece of the big rectangle that's in between the two squares, right? And of course, the two squares, their predecessor was the empty set. So you end up with the attracting neighborhoods for those because they're minimal attractors. And when you look at when you do that on the level of the attractors, then the set difference on the attractor level, where you look at what is the dual repeller of the union of those two equilibrium points, you get the saddle in the middle, right? And so this is what is a Morse decomposition. So you have these poset of invariant sets in your underlying system called M of A. That's what we call a Morse representation. And what's the difference between a Morse representation and a Morse decomposition? Well, in a Morse decomposition, you want to be able to have the freedom of allowing sets to that you're looking at to have an empty invariant set inside of them, because things can bifurcate to the empty set. And this is part of Conley's original definition of a Morse decomposition. And the way you resolve that in this order theory is that a Morse decomposition is an embedding of the actual empty, non-empty invariant sets that you get from this construction into some poset that has a meaningful order. And the poset that has the meaningful order is this poset of the isolating neighborhoods, right? And in this case, as I said, they're isomorphic because I constructed it that way. But when you start from just a decomposition of the space and you try to identify attracting blocks, and then you do this construction, there's no guarantee that this thing is going to be an isomorphism, right? It's just going to be an embedding. And as I said, I'll do an example in a moment. Okay, so the big takeaway message is that we hope that we could compute these attracting block lattices because they're attracting blocks because they're robust. And from that, we can get posets of isolating neighborhoods of what should be Morse decompositions, right? And these structures are robust. If I tweak the system, then these structures still remain, right? Okay. We can also go backwards. So we went from the lattices to the posets. You can also go from the posets to the lattices, and I'm not going to spend a tremendous time on this, but basically if I have a poset and I look at the downsets, so I look at an element and I look at everything that lies below it, and then the collection of downsets of a poset form a lattice. And as Burkhoff's theorem, this is a well-known theorem, that these things are isomorphic. So basically, a finite bounded distributed lattice is completely dually equivalent to a finite poset. So how do we actually try to compute these things? So we have we want to construct what we call a combinatorial multi-valued map. So you can think of this as a directed graph or binary relation where each cell in some sort of decomposition of your space is a vertex in the directed graph or an element in the binary relation. And the edges of this graph are representing the images of that cell under the dynamics, right? So I could think of making, trying to make some sort of approximation of the image of one of these squares by a union of other squares, right? Or if I'm in the flow case, like on the left, I could think of trying to flow from one triangle to another, right? And use that as a mapping, multi-valued mapping. Okay, so one thing that is kind of an interesting result, that this is with Rob Vandervorst and a graduate student of mine, is that whenever you have, like we have here, a finite collection of two finite lattices, bounded distributed lattices, and a surjective homomorphism, there's always a binary relation or a digraph F that you can realize that homomorphism in terms of attracting blocks and attractors in a combinatorial sense, right? So we have our underlying dynamics that we want to compute, and we're going to build, I'm going to explain in a minute how you can build these multi-valued maps. But what are we going to do with these multi-valued maps? We have to still pull out these same sorts of structures, okay? And so the structures that you get from these finite directed graphs, you're looking at attractors, which are sets that when you look at the multi-valued map image of an attractor, you get the same set back. And when an analogous thing to attracting blocks are the forward invariant sets, namely ones where you apply the multi-valued map and you move forward and you are a subset of what you started with. Okay. And so it turns out that no matter what homomorphism you start with between lattices, it could be realized by one of these directed graphs and as attracting neighborhoods and attractors. Okay.
What is this condensation operation?
So it's kind of the thing that we do when we have posets's is that when you extend a digraph by say transitivity, right, then you're not really changing asymptotically what's going on, right? You're just adding edges that can be reached in multiple steps. And condensation is meaning that if I have a cycle in my graph, then I condense that down to say a single element, right? So
strongly connected components. Is that what we are talking about?
So yeah, so it right. I will get to that in just a moment. So
okay,
this can be explained. So when we do the dual objects on the combinatorial level, you're going to be looking at strongly connected components and then what we call recurrent components, where you have strongly connected components with a non-trivial edge in them. Okay.
Okay. Thank you.
Yep. Okay. So so we could try to represent this multi-valued map as a state transition graph, right? This is the idea. So you're trying to approximate the dynamics by saying where is some, let's say, box. I'm going to talk in terms of boxes and cubical complex. Where is this box going to go? So here I want to give a very explicit, these lattices can grow very quickly. So I want to give an explicit example in a picture. So I'm only going to take the previous example and add two boxes to it. So I'm going to add a green box to the top left and a green box to the bottom right. And those, the multi-valued map are what the red arrows are here, right? So each of the blue boxes that have an equilibrium point in them are mapped to themselves. And then you see the middle one has saddle behavior, it maps to the other two. And then the green boxes map down into the equilibrium points on the other side. So this would be a multi-valued map. And we can look at its attractors and we can look at its forward invariant sets. And we can ask, what do we need in order to say that when we do that, we really have attracting blocks in our underlying system and attractors in our underlying system, right? And that's what I want to talk about next. That's what we want to think about. But let's just look at what the picture is so you can envision what these lattices look like. So this is the entire forward invariant set lattice of this system. And you can see it's starting to grow fairly large. And it has 5 joint irreducible elements that I circled here, right? And if I take omega limit sets on the combinatorial level, I get down to the original graph that I had before, right? The original lattice that I had before, which is happens to be the attractor lattice in this combinatorial system. And so this is
I'm sorry, I'm having trouble interpreting the green additional boxes. Could you just again explain what I should be thinking about?
Sure,
when I see
sure. If I go back to the original picture here, so if you think of the blue box here on the left, if I put a little box above it, right? Where is it going to go? It's going to map into the blue, right? Does that make sense?
I get to choose them or you choose them?
Well, if I wanted to analyze this system, I would take a big rectangle and I'd put down a bunch of boxes, which I will show you in a minute, okay? But if I try to do that, I'm not going to be able to show you the lattice, right? So, because it'll be too big. All right. So, So this is what these lattices under the hood are looking like. They get too big to picture, but I just wanted to show it to give an idea of what's, what you should be thinking is going on in the background, right? And when we look then at the underlying joint irreducibles, then of the big lattice, there are 5 joint irreducibles that I circled here. And then of the attractors, there's only 3, right? So we get an embedding, right? So here's a case where it's not an isomorphism, it's just an embedding. We have, we have these other joint irreducibles because of the green boxes, right? And when you apply the Conway form to these things, then what you end up with is exactly what, I forget who asked the question, is exactly the strongly connected components in this directed graph, right? So the green guys are their own strongly connected component, and they have no edges in them, right? They're just a single vertex in this graph. And then the other 3, the blue ones, they have an edge, right? They have a self loop. So those are, we distinguish between the strongly connected components that have no cycles in them, no self loops, or not contained in a cycle, versus ones that are cyclic, that have some sort of self loop or are on a bigger cycle. So we call the ones that are on a cycle the recurrent components, and the ones that are not, and then all of them is the strongly connected components. Okay. Okay, so to be specific, SC of this combinatorial map is the post set of equivalence classes and the grid elements where you're looking at connections. So this is just the strongly connected components. And when you look at realizing those things as sets in your underlying topological space, then you get a post set of sets, right? And that's what we are calling T of n. N is the realization as sets of the attractor lattice, and then T of n would be that stands for tiling that you get by applying the realization map to the strongly connected components. And then as a sub-post set of the strong components, you have the recurrent components. So those are the ones that have at least one edge in them, self-loop, whatever. So what turns out is, the way to understand this is, the strong components are the joint irreducibles of the forward invariant sets in this graph, and the recurrent components are the joint irreducibles of the attractor. And so you have this duality where you have omega mapping forward invariant sets to attractors, and you have the what ends up being the inclusion map of the recurrent components to the strongly connected components. And as Constantine said, it's very efficient to find these things. There's linear time algorithms, Tarshan's algorithm, for finding these types of structures. Okay, okay. So so as I said, we use this idea of a realization map. So to go between this kind of combinatorics of saying we have, vertices and edges in a graph, to we have sets in a topological space, the phase space of our system. And the idea that we would like to understand is that then in that context where we look at this realization map, and sometimes I write union, I just realized, that should be with the bars there. So if I realize a forward invariant set in the graph, then that's an attracting block in my underlying system, right? So the idea is that you want to create a state transition graph, a multi-valued map on these cells in such a way that whenever you take something that's forward invariant in this graph, then that's an attracting block when you realize it in the topological space. Okay, and there are a variety of ways of doing that, and which I will describe. There's a couple different ways of doing that and assuring that that condition holds. And then the question becomes, what can we extract from that, right? So if I just declare these I have this lattice of forward invariant sets on these cells come from this directed graph. I declare that those are going to be attracting blocks for whatever system I'm trying to study. Then what can I say about that, right? So one way to construct something for which the statement that I just made is true, namely that the forward invariant sets are attracting blocks, is to construct something that's called an outer approximation. This goes way back many years. Andrei Shimshek came up with this notion. So the idea here is basically you take whatever the true image of the cell is of your underlying system, little f, and you rigorously cover the entire image by boxes, right? Then you're not, in this situation, whenever you have an orbit in your underlying system, you have to have a walk through your graph that contains that orbit, right? And so you're not losing any recurrent behavior. So anytime your dynamical system would have a periodic orbit or some other recurrent dynamics, then you are going to find in your graph some sort of cycle. Okay, and so this is this idea of an outer approximation we've used quite a bit to try to understand to get this idea that going the wrong direction, to get this idea that forward invariant sets correspond to attracting blocks, right? And so then you can ask, well, I could think of a model then as saying, well, forward invariant sets in my directed graph are attracting blocks in my underlying system. And of course, I can look at attractors for my graph. And of course, once I have a lattice of attracting blocks for my system, I can look at the attractors in the system and by applying omega in both cases. And what does this tell me? Can I relate the attractors of the multi-valued map to the attractors of the underlying system? Can I get Morse decompositions, right? So what can I extract from this? And all you need to get this combinatorial model, outer approximation, is actually too strong. All you need is something we call a weak outer approximation. You just need to cover entire forward orbits instead of specifically first images. So the problem is that if I try to get a map across the bottom between attractors in my combinatorial system and attractors in the real system, I can get such a map because any attractor in the combinatorial system is forward invariant. So I have the inclusion map that goes up on the left, and then I can follow it around to go across. But the problem is the inclusion map doesn't need to be a lattice homomorphism. So what we want is a lattice homomorphism between these things. And why doesn't it have to be a lattice homomorphism? That's because, as I told you at the beginning, the wedge operation on attractors isn't intersection, right? It's omega limit of the intersection. And so you can see an example down at the bottom where the intersection is not the same as the wedge, right? So it turns out whenever you have an outer approximation, then you're good to go. There is a natural connecting homomorphism across the bottom, which is omega of the realization. But in other cases, if you don't have an outer approximation, that can be harder to determine, right? So I'm going to do an example in just a second. Sorry, I have to say one more thing. So this whole picture of a combinatorial model can be dualized from the lattices here on the left to the posets on the right, right? So you think of forward invariant sets of your directed graph. When you dualize them, you get strong components. When you dualize attractors, you get recurrent components. When you dualize the attractor lattice, you get a Morse representation. And when you dualize the attracting blocks, you get some sort of tiling. And this will be very explicit in just a second. I probably should have put the example a little sooner. So what we want to understand is, if we want to think of this in terms of Morse decompositions, the thing that we can understand is not M of A. We can't get our hands on the attractors or the actual Morse sets. What we can get our hands on is the T of N, the tilings from the attracting blocks, right? The dual of the attracting blocks, because that's what we specified in our model, right? So let me do the example. So here is an example of a two-dimensional map. This is a population model that is a nonlinear Leslie model. And it has some fairly complicated dynamics. So there's several periodic points. The R2 here is a chaotic set inside of there. The R1 is some sort of invariant circle inside of there. If you really did precise numerics, which is done by Ugar, Savici, and Weiss, you can look at their paper. They do a lot of very careful, precise numerical simulations. But here, we're just looking at this, as Constantine said, with much more coarse grain eyes, where we just want to identify where there are recurrent parts of the dynamics and what the order between them is, right? So we're trying to identify some sort of Morse decomposition. So what I did here is I divided up this rectangle from 0 to 70 or 80 up to, and cross 0 to 55. I divided up into millions of boxes, and I compute an outer approximation rigorously using interval arithmetic on the explicit formula for the map. And I look at what the recurrent components are, the strongly connected components in that graph that have an edge in them, a non-trivial edge. And I get these 6 regions. And what you see here is, for example, R4 has 3 parts. And if you kind of look at what happens on R4, they kind of map around. It looks like a period 3 orbit. If you were to look more carefully at what happens to the multi-valued map on R2, you could try to reconstruct and see that there's chaotic dynamics in there. So if we were to apply Conley indices to these things, we could try to reconstruct the dynamics on the inside. That's not what I'm going to talk about. I'm going to talk more about the order theory, right? And R3 here is hard to see. It's just a few boxes that are at the tips of R2. Okay. And when I look at what do I want to do? I want to somehow look at use the attracting block structure, right, of this entire multi-valued map with millions of strong components. So all of the other boxes that are not colored in this picture are single element strong connected components, right? So if I look at this graph, the strong components of F are huge, right? And so if I want to see what's happening in the entire rectangle as compared to these recurrent components, then I need to somehow identify what's happening with those other strong components and retract them down to the recurrent ones. And so that's what I'm trying to indicate in this picture, is that if we somehow are able to have a homomorphism between the attractors of the combinatorial system into the forward invariant sets, it's this thing lift on the left L, that's dually equivalent to having a retraction of the strong components onto the recurrent components, right? So if you can take all of the strong components, all the rectangle, all the boxes in this white region in this picture, and identify them to a particular recurrent component and maintain the order, right? Then you're reducing down to just looking at the recurrent parts of F, and that simplifies your picture. So instead of having, so in this picture, if you ask me what Morse decomposition can I find here? Well, if I didn't, I know that this is an outer approximation. So I know that the white regions here don't have any recurrence because outer approximations can't mask any recurrence. But if I just said, if I didn't know that this was an outer approximation, I was just doing some arbitrary approximation or some sort of getting it from data or something like this, which I'll describe in a minute, then I don't know that there couldn't be recurrent parts in the white region. So the best thing I could tell you about a Morse decomposition is that you can identify the boxes in these 6 regions together, and then all the other boxes could have a recurrent part in them too, right? Could be part of the Morse decomposition. It doesn't happen here because we have an outer approximation. And you can identify all the boxes that are by this order retraction algorithm that Rob Vandervorst and the graduate student that I talked about earlier. We have an algorithm that identifies how to do an order, when an order retraction exists. It doesn't have to, between the strong components and the recurrent components, and then how to identify them. And so what you see in this picture is each of these recurrent components that I had colored before, these are the boxes that I get identified to those. And these are essentially the boxes that get mapped going forward by the multi-valued map into those regions, right? So you see like the red region here, the red recurrence set was a period 3 sort of orbit. So you could think of this as an approximation of the stable manifold of that thing in some sense, right? And the same thing with the other ones, right? Do I know that that the inside each of, so these are isolating neighborhoods in the underlying system, right? From the Connolly form. Do I know that each one of these contains some sort of non-empty invariant set? No, I don't know that, okay? That's something that we can't get our hands on the Morse representation. We can only get our hands on this tessellated set, right? So this tells me that there is a Morse decomposition for this system that has at most 6 non-empty Morse sets in it, and they're compatible with this ordering, right? But I don't know for sure that all 6 regions have a non-empty Morse set inside of them, okay? I can use the Connolly index, for example, to check that. And it turns out that in this small little light blue region, there is in fact, the Connolly index is trivial, and we may not expect that there is something in there. So what we could do is then retract down further where we move R3 onto R2, and we only look at the Morse decomposition with combining R3 and R2, and you would get isolating neighborhoods in this lower right picture. And here you could check by the Connolly index that all of these things are non-trivial, so they all have Morse sets in them. So there is a Morse representation, non-trivial Morse sets with this order that goes by these colored tiles in this system.
Bill,
yes.
You're basically out of time.
Yep.
Okay.
So I will maybe end there. I'll just say that one thing that we are doing that Everton will talk more about is kind of looking at what you could do from data. So, you know, if I have a simple bistable system here and I want to sample it and look at it from data and come up with some multi-valued map, some way of looking at where boxes go based on these data points, right? And there's a variety of ways of doing that. You can look at nearest neighbors, you can look at surrogate models, things like that. Then you could talk about whether or not there's an order retraction onto the recurrent parts that you find here. So here's an example where, you know, I sample a few points, 50 points of this system, and I do get some sort of order retraction onto the recurrent parts. And then here's an example where I don't. And one of the things that, you know, you could think about is that the places where you don't have an order retraction, that's telling you that the dynamics don't fit together right? That whatever combinatorial model you made, you did identify some recurrent parts and some isolating neighborhoods, but it doesn't, your entire space is not able to be retracted down onto those. So you may want to sample more in this region or figure out why something is going wrong in that region, right? With your how you created the model from your data. And with that, I think I will stop. Sorry about the technological mix-up at the beginning.
Thanks, Bill. Let's take one or two really quick questions so we don't get too far behind schedule. If there aren't any immediate questions, Dan.
Bill, if I cared only about attracting sets and didn't really care about the chain recurrent set above the attracting sets, does that make these computations any different? Can I search for nearly the bottom of the Lyapunov function, or does that not make it any easier or harder?
So looking only at the minimal the minimal Morse sets, so that they're attractors. I'm not sure that so when you apply the kind of Tarjan algorithm to the entire multi-valued map, you're going to get all of the connected components, right? And so and you're going to get the order structure. I guess one thing you could circumvent is one thing that's not quite linear time in theory, but is often fast in practice is the reachability of the entire, which Morse sets, which recurrent components can reach other ones, right? So then you wouldn't have to do that reachability computation if you're just wanting the bottom ones, right? Most likely, but yeah.
Anyone else? Okay, I suggest again, we take a 5-minute break and start at 5 minutes after with Yuli's talk. Okay, thanks, Bill.
Yep.